It's a nice little role reversal from last year. I got to introduce you. You're introducing me this year. So
right.
There we go. There we go. All right. Thanks, everybody. It's great to be back. Great to be in person here for the Flight Software Workshop. I'm the Flight Software lead. I'm Brandon Haber for Dragonfly. It's a New Frontiers mission to Titan, Saturn's moon Titan. I'm presenting a large amount of work on behalf of several members of my team, but notably Amy Alford, who couldn't be here today. And so I'm going to go ahead and dive right in. So for the outline for this talk, I'm going to talk a little bit about the mission overview and context, give some motivation for some of the work that we're doing, and then I'll talk a little bit before I get into the compression side about our flight software design considerations. APL has a very long history of heritage flight software, and so in order to understand where our design went, you kind of have to understand a little bit about where we started. So I'll talk about that in a high level, and then I'll dive really into the meat of this talk and talk about our compression trade study and some of our trade study results, and then talk about where our design has ended up and what some of our conclusions were and maybe some applicability that we may have to other missions. So just real quick, Dragonfly's destination is Saturn's moon Titan. It has a very low gravity. It's about 1/7 gravity of Earth's. It also has a very dense atmosphere. So talking a lot to the Ingenuity people this week, we have a much lower gravity even than Mars, but a much denser atmosphere. And so our craft that we're designing is a rotorcraft designed for heavier than air flight on Saturn's moon Titan. And it is very easy to fly on Titan, energetically speaking, of course, not from a complexity or design perspective, but from an energy perspective, it's very easy to fly, even compared to Earth. And of course, it's very cold there, very far from the sun, which introduces thermal challenges that I'm not going to talk about at all today because it doesn't really affect the software. So for our flight system elements, got some pretty pictures here. So we have our spacecraft, looks pretty standard for any other sort of planetary missions. We have our spacecraft. It's got a crew stage on it. Crew stage has all the traditional spacecraft stuff. It's got propellant tanks and thrusters and sun sensors and star trackers and all of that. We have an entry vehicle. It has back shell and parachutes and a heat shield and all of those things. But then inside that entry vehicle is something that looks pretty crazy. It's that octocopter that you see there over there on the right. That's our heavier than aircraft. It has some things that a lot of spacecraft don't have. It's got rotors, it's got landing gear, it's got all that fun stuff. But the big thing that's relevant to this talk is you can see in the middle there, that's our high gain antenna deployed. And it's actually very similar to the one shown earlier today for DART, the radial line slot array. And that antenna, of course, has to be carried with us as we fly. It has to fit within a heat shield. It's got all those constraints. So when we get to our mission here, let's talk a little bit about our downlink. Dragonfly is very, very downlink constrained, extremely downlink constrained. And there's a lot of different reasons for that, several ones. So first of all, Saturn's far away. That's probably not news to anybody here. But we have those mass, power, and volume constraints, right? We want to be able to fly long distances. So it's not even just about the launch vehicle and fitting on the launch vehicle. The heavier we weigh, the less far we can fly each time we want to fly on Titan. We also have those volume constraints, right? We can't just package some huge antenna that takes up half the side of our spacecraft. We need to be able to fold it down. We need it to be able to not be flapping in the wind as we go fly around Titan. So it's something that ends up having a lot of volume constraints on it as well. We also don't have that relay fleet that all the Mars rovers have. You guys are lucky, anybody that works on Mars, having that relay fleet. We have to talk all the way back to Earth, direct to Earth, all the way from Saturn with all of those mass and volume constraints. But the other thing there, that fourth one is one that matters just as much. It's maybe not as appreciated, but we have that operational cadence, similar in some ways to the rovers. We want to analyze a site and we want to downlink the data, and then we want to move on to the next one. We want to fly to the next place and take a look at that and look at the next place, go over the next dune, go look at the next crater. For some previous deep space missions, for example, like the New Horizons mission that APL built to Pluto, we could spend a couple of weeks flying by Pluto and just storing tons and tons of data on our recorder. And then after that, we can spend a year and a half pointed back at Earth, downlinking all of that data because there's no Pluto a week later. There's no second Pluto or third Pluto or fourth Pluto. The next flyby was years later. And so you could spend all of that time downlinking your data, but we can't do that. We want to downlink our data, and then we want to get on to the next place and get that data back down. So the result of all of these things, and our draft trajectory there is that we have that very constrained downlink volume, right? And so the more we can do on the flight software side to get more data down to the ground is more science, more understanding of Titan. And so we started a trade study to say, okay, how are we going to meet this? How are we going to use the flight software in a way that can benefit the mission operations, benefit the science, and everything else? But before I get into that, a little bit about where we started from. That's our heritage flight software. Like I mentioned, APL has a very strong history, very strong heritage in flight software. Some of it has impacted asteroids, as we saw earlier today. Some of it's flown by Pluto or touched the solar corona. And so this is what that looks like right now in terms of our nominal command and telemetry path. We use the Core Flight Executive, not the Core Flight System, but we do use CFE. Dragonfly is currently on CFE 6.7. And we make very extensive use of CFDP, reliable mode for both uplink and downlink. And so our ground system sends up files with CFDP, and these files there, as you can see on the bottom left, will have a series of commands in them. And we can send those up with CFDP, those go onto our file system, and then a file ingest application can then scan those files and send those commands on to their next destination. Almost nearly symmetrically, on the downlink side, we can record all of these telemetry packets that come from whatever other application or subsystem we have in the vehicle. Those can be recorded to a file system, and then the CFDP can downlink all of those. One thing that is important as we get into the compression trade study, though, is that record application up there on the top right has a very large amount of configurability. So we can sort different telemetry packets into different files. And so depending on what set of files you're looking at there, that set of files can have a totally different set of telemetry in it over time, or even at the same time, we can be recording a dozen different files at once with different sets of telemetry. And that's important as we get into our trade study results. So when we started here, we knew we had all the science data, we knew we had all the spacecraft housekeeping data, we knew we needed compression for something, but what were we going to end up doing? We knew this compression, by the way, it needed to be lossless and it needed to be generic. So all of the really awesome stuff that we've seen so far this week about neural network-based compression and lossy kinds of compression, that was pretty much a non-starter for us right at the beginning. We knew we needed something that could be lossless for things like our spacecraft housekeeping telemetry. So our compression trade study methodology here, we started off by analyzing really 9 different options, and I'll talk a little bit about each one. And this was really just our starting point that we looked at, and we considered various expansions and other options, but this is really what we settled on as well. We looked first at 3 different open source algorithms, right? So BZIP to GZIP and LZMA or the XC algorithm. And then we looked at 3 different windowing sizes, and a little bit about the windowing sizes there. When we were looking at compressing data, if we have a file of TC packets, of telemetry packets, we could compress subsets of those packets and say we're going to compress 4096 packets or 4096 bytes of data, compress that down, and then still put another packet header on the front of that. And so when you actually looked at the file, you'd still see a file of telemetry packets, and that telemetry packet would just say, hey, there's compressed data in here that may be multiple packets inside of it. And so 4K bytes is actually the max packet size that we traditionally use. And so that was one of our starting points for our windowing size. We can compress up to 5 kilobytes at once, and then we compress another 4 kilobytes and on and on. CCSDS, though, does give us a 16-bit packet size. So we looked at, well, maybe we're going to take a similar sort of algorithm, but we're going to compress up to 65K at once, right? So we're going to take up to 65K of data, and then we're going to compress all that down until we get to that. But the other option that we looked at was just compressing whole files at once, right? So there's no visible packet headers in the underlying data. If you were just looking at the file as it was in the file system, it's just the whole thing's compressed. And so conceptually, it's a lot like, you right-click a file on your desktop and then you hit the zip button. That's a lot like conceptually what this was going to look like. And we did have a past APL mission that we could compare against that used the GZIP algorithm and 4K byte packets. So we could kind of validate our analysis pipeline a little bit against the real results from that mission. And then we also decided to be consistent. So all the following graphs that I'm going to show you show our compression results as a percentage of the original uncompressed size. So we say, 50% compression instead of 2x or so on and so forth, 25% instead of 4x. So on to the results. This is a big amount of data here, so I'm going to talk through it, and hopefully it'll make sense in a few minutes. The x-axis there is those 9 different options that I was telling you about there. So on the far left, you can see 4096 BZ2. So that's saying, you know, if we use the algorithm of up to 4 kilobytes of data and the BZIP2 algorithm, then those are the compression results that you get for all of those different kinds of file types. So remember I said our record application can sort different kinds of telemetry into different file types. And so if we have the 2FA file type or the 1FI file type, okay, you get really different compression results there on the y-axis. This is real results. This is real spacecraft housekeeping data from a mission that doesn't have a compression service. So what we're looking at here is, okay, if we had, let's say on the very far right, if we just used whole file compression and the XZ algorithm, this real mission that APL is operating right now would be able to save a really tremendous amount of telecom bandwidth on their spacecraft housekeeping data. Their spacecraft housekeeping data would be 16% of its original size, right? So over 5 times compression ratio. With no other changes, right? So completely lossless compression algorithm, no other changes to the underlying software, but you could compress all that down, get over 5 times as much engineering data down to the ground for the same telecom system, the same DSN time, same power budget, and all of that. So one of the things we discovered here with those black dots in particular is the weighted average over the whole data, is that windowing size has a huge effect. And maybe this kind of makes some intuitive sense. Okay, you can take more data at once and you compress it and that goes better. Well, okay, sure. But when seeing this against real data, we really started to think, okay, well, you know, we had this mission constraint that we had to be able to use partial files if they got downlinked, if we missed a hole, even if CFTP could fill it in later. Maybe we want to rethink that. Maybe we can get really big gains if we went up to that whole file kind of compression option for Dragonfly. But you can see there, if we're compressing only 4 kilobytes at once, you're still even able to get some pretty big gains, right? You still get, you know, a third of your original size. You can still save maybe half of your telecom budget on engineering data, or get twice as much engineering data down. Even with that. But even going to whole file compression, again, with these open source compression algorithms, you're able to get, you know, something like 4 times, 5 times the engineering data. And again, this is from a real mission that APL is operating. But then, of course, it's not all about engineering data, even though we're mostly the engineers. There has to be some science data that comes down too. And so we took a look at some science data. We asked our instrument friends and said, okay, do you have engineering benchtop data, or do you have an instrument that's flown on a past mission, perhaps, that is somewhat analogous to the instrument that you're building on Dragonfly? And many of them said, yeah, sure, okay, here's some data, right? And so this is science data from a past mission, real flight data, real flight science data from a similar instrument that will fly on Dragonfly. And this mission didn't have any sort of compression service, and so we kind of crunched on it, and we said, okay, wow, this data is really compressible. We can really, you know, even completely losslessly, we can get a lot more out of this. Even at really small compression windows, you know, the lowest, least performing option that we looked at there, that 22%, that's over 4 times the science data you could bring down from this instrument on the same telecom budget. But even as you go down all the way to that whole file compression, you're able to get, you know, almost 10 times as much science data down from this particular instrument. And this particular science instrument is actually predicted to be one of our larger data hogs on Dragonfly. So hopefully, you know, that past science mission and this and the science payload that we're actually building for Dragonfly will end up having similar data patterns, and we'll be able to get, you know, really large amount of science data down, more than we were originally predicting. When we started ending up looking at this, we said, well, you know, we're doing CFTP on the uplink too. What would, you know, wasn't originally in our scope, you know, in our proposal that we were planning to do compression on the uplink. But, you know, it's still files, right? It's still files. So maybe we should compress those as well. So we did this similar thing. We looked at all of our command files that were going up to a real mission that we're operating, months and months of data at a time. And we said, all right, well, these all have different file sizes. You know, some uplink files are like 500 bytes and others are hundreds of kilobytes, you know, representing weeks and weeks worth of operations. And so, you know, how much could we end up compressing them? And the answer is still quite a lot. you know, even with really small files and even with our least performing compression algorithms, you might be able to get a 2x gain on your uplink. You might be able to get a 3x gain on your uplink as you go to the higher performing options, compressing whole uplink files at once that may be kilobytes or hundreds of kilobytes. And so, you know, we looked at this and we said, hey, you know, program, can we get a little bit extra money to go do this? And they said, yeah, sure, definitely. Right. This was a big win for a very constrained uplink, similarly as a very constrained downlink for our mission. But one of the other things that we realized as we took a closer look at some of this data was some of the variations in the underlying data. So these are two graphs for two different file types, right? So again, real APL mission, looking at the file type 1_FD. And so this is a particular mapping of telemetry packet app IDs, CCSDS app IDs to files, and then another file type, the 0FP file. And for the 1FD file, for whatever underlying data is in there, that compression ratio is very, very stable over time. So that file, whatever's going into it, you know, from 1 month to the next or 1 week to the next or whatever, that compression ratio is really solid. So if you're trying to plan downlink for your mission, wow, okay, that's, you know, you can plug that into a planning tool and you can have a pretty good idea that you're going to get a really good compression ratio on that. That's going to be really solid over time. But whatever we're recording in that, you know, 0FP file type, whatever telemetry is going into there, wow, that's huge variation, right? Week to week, day to day, month to month. There is huge variation in that underlying data for whatever reason. Sometimes the compressed file type might be 4 or 5 times different in underlying size on your downlink budget. So if you're trying to plan downlink for this mission, you've got to understand that. You've either got to know that maybe it's going to take a little longer than whatever average you're planning, or maybe you've still got to be really conservative and say, this is high priority data, I really want to bring it down, and so I need to plan for the worst case, even though the average case might be way better and you're going to get it down in half the time or a third the time or a tenth of the time that you originally thought. So a little bit more on windowing size. And so these are 4 graphs of the same data, but different x-axis on each time, from top left to top right and then bottom left. So for all 3 algorithms, right, each of those colors graphs there is one of the different compression algorithms. You could still get small gains at low windowing sizes. So maybe you have a really small amount of RAM, or maybe you just have a really small amount of data that you're compressing in the first place. You can still squeeze a little bit of compression out of it, right? You can still maybe get 2/3 of your original size, even if you're only compressing a few hundred bytes at a time. But as you get to larger file sizes, as you get to more and more data that you're able to compress at once, the knee in the curve that we found in our engineering data was really around that 100 kilobytes kind of time frame, where you start, you know, the knee in the curve starts flattening out. And so this affects a lot of our planning. This affects how much data we're recording when we're choosing to downlink it, especially for some of our lower priority data that we can wait a little bit more on. From an operations perspective, we're saying, well, we'd like that data down, but maybe we're just going to keep collecting it for another week, right? And then we're going to compress it all at once and then bring it down later, because the end result will be fewer bits on the downlink. The values and ratio here aren't important, of course. They are completely affected by whatever underlying data you're actually trying to look at. But there will be a knee in the curve if you're looking at something like this for your mission. There will be in the knee in the curve. It will be at a different place for whatever underlying data you have. And that's something to look at if you're looking at doing something similar. So where did all this end up then? So we ended up choosing the whole file algorithm, windowing size, and the bzip2 compression algorithm. It looked like the easiest algorithm to integrate. It was on the middle of the performance of the 3 algorithms on the whole file size. We ended up persuading our mission operations and systems team that we should be okay with partial file loss, you know, and temporary holes. We are using CFDP class 2. The holes will be filled in eventually, but potentially on a future downlink pass. So the mission was originally not okay. We had a requirement that partial files needed to be usable, but we ended up backing off on that requirement because of the big downlink gains that we could see here. And so as systems mature, as engineering models are built, as flight models are built, as we get analog science data results, we will continue analyzing that higher fidelity data analogs to feed into our downlink modeling. So we can tell our mission operations team, we can tell our ground software planning tools, you know, we're going to go record this much data, and here's where it's going, you know, here's how long it's going to take to come down. We've also done some benchmarking. So on our flight computer, BZIP2 can compress about 3 megabits per second of source data. That is 2 orders of magnitude faster than our fastest downlink rate from Titan. So we're pretty sure that a low priority background task is going to be more than sufficient to keep up with all of this downlink, right? And so depending on your mission, if you're looking at something similar to this, you may have a different ratio of CPU performance to downlink rate. There may be a different answer for you there. But for us, a couple percentage points of our CPU is going to be more than sufficient to keep up with all of our downlink rates and be able to compress all of our downlink data. So where did this end up on our design? Well, we kind of put a file compression application right in the middle of both sides of our pipeline, right? And it's the same CFE app for the file compression app, and it can notice when files need to be uncompressed for the uplink. A compressed file has shown up on the uplink, and then we uncompress it, and then it goes right to the same pipelines that it did before. And same thing on the downlink. Our record application can still work almost exactly as it did before. The only exception is a little flag that says, is this something that needs to be automatically compressed or not? And we expect to enable that for the vast majority of our files, but maybe for certain things we decide not to. And then that new file notification just goes right down to our file compression application, and it would have a background task that'll churn on that. And CFDP never cared about the file contents anyway. CFDP never cared whether there's telemetry packets or command packets or compressed data or uncompressed data. So it just gets a whole file and downlinks it down to the ground anyway. And then the ground software knows that it's compressed or not based on the file name in CFDP, and can then uncompress it and send on telemetry back down to the ground anyway. So we're able to take a pretty surgical approach to this and maintain a lot of our heritage software even as we put in this new capability. So in conclusion for this, compressing lots of data at once can provide large gains on downlink constraint missions. This seems like kind of an obvious conclusion, but it's still nice to see the data bear that out. We already have the abstractions for a file system and CFDP, and so that provides a pretty conceptually similar form for this. It doesn't take a lot of explanation to mission operations to say there's a file and it gets compressed, right? Everybody's pretty familiar with doing this on email or whatever else. And we expect flight software to provide large gains for an otherwise extremely downlink constrained mission, bringing in more science and more data back from Titan. So that's all I have, and ready to take questions. Thank you.